At Caltech, Dionne and colleagues created a bizarre optical material in which light bends backward. As light passes from one material to another, say, from air to water, the rays are deflected due to a property called the index of refraction. That's why a straw in a drinking glass appears to be broken at the water surface. In natural materials, light always bends in the same direction. But that rule gets flipped around in oddball nanomaterials with a negative index of refraction. Dionne's material, reported in Science in 2007, was the first that worked with visible light SN 32407, page 180. Because they can steer light around objects to hide the objects from view, such materials could be used to create rudimentary versions of invisibility cloaks, though so far all attempts are a far cry from Harry Potter's version. Dionne is now working on a squid skin with an adjustable refractive index, which would mimic the shifting camouflage patterns of the stealthy cephalopod. Another focal point of Dionne's research is harnessing light to separate mixtures of mirror image molecules. Right and left-handed versions of these molecules are perfect reflections of each other, like a person's right and left hands. The two types are so similar that scientists struggle to separate them, which can cause problems for drug makers. In drugs, these molecules can be two-faced. One might relieve pain, while the other causes unwanted side effects. To separate molecules in their mirror images, Dionne is developing techniques that use circularly polarized light, in which the light's wiggling electromagnetic waves rotate over time. Such light can interact differently with right and left-handed molecules, for example, breaking apart one version while leaving the other unscathed. Normally, the light's effect is very weak. But in a theoretical study published in Axe Photonics last December, Dionne and colleagues showed that adding nanoparticles to the mix could enhance the process. These tiny particles behave like antennas that concentrate the light onto nearby molecules, helping break them apart. Dionne is now working to implement the technique. She and her colleagues have also created nanoparticles that, when illuminated with infrared light, emit visible light. The color of that light changes depending on how tightly the nanoparticle is squeezed, the team reported in Nano letters in June. In keeping with her penchant for creative exploration in the lab, Dionne and colleagues fed these nanoparticles to roundworms, the nematode Canorhabditis elegans, to study the forces exerted as a transparent worm squeezed a meal through its digestive tract. You can see the nanoparticles change colors throughout, Dionne says. She plans to use the technique to reveal more sinister squeezing. Cancer cells exert stronger mechanical forces on their environment than healthy cells, so such nanoparticles could one day be used to test for cancer, she says. Dionne is now cooking up other creative ways to use these nanoparticles. In collaboration with other researchers, she hopes to marshal her color-changing nanoparticles to understand how jellyfish move and how plants take a drink. Dionne's work exploits light to reveal hidden forces, and as a force for good. She's done amazing work, says material scientist Pranihai Narang of Harvard University. Narang was a graduate student at Caltech after Dionne left, and had heard chatter about Dionne before meeting her in person. The legend of Dionne was definitely all over, Narang says. So Dionne has made a start at establishing her scientific legacy, even before that chat with her future grandchildren.